Okay, so I would say we can start. Can you all hear me and see the slides?
I can.
Okay, perfect. Thank you. Okay, then welcome everyone to the core training for the course test theory. Now, before we begin, I would like to ask you if you could turn on your camera. Obviously, I'm not going to force you to, but as you can see, we are very few people, so it's always nice to try and make it a bit more interactive. And obviously, it's also a direct way for me to get feedback in terms of if you're done with your exercises, if I see very confused faces, and also for you to give me any direction, as in, like, I don't know, I have a question, you can just raise your hand. So if at any point, if you're having breakfast, maybe once you're done with that, you want to turn it on, that would be very much appreciated. Okay. So before starting, just to very quickly introduce myself, my name is Alessia. I did a Bachelor of Psychology at Tilburg University, and then I did a Master in Clinical Psychosexology. I've been teaching for the last 5 years, mainly statistic courses. So you're gonna see me teaching test theory. Next semester, you're probably gonna see me teach experimental, and in your third year, applied. So all these statistical courses. Now, why am I teaching them? Sure, I got a good grade, as you can see, but mainly because I'm one of those few rare people that do love statistics. So now I don't expect you to feel exactly the same way. I realize that I'm the crazy one, but if after today you hate it a tiny bit less, that's already a pretty good achievement, in my opinion. Okay, so what is the structure gonna be for today? And that's in general the structure that you'll find at any Athena courses. So sure, it is a statistic course, but theory is still very important. So you're gonna see also that at the exam, more or less, half will be about theory, half will be about calculations. It can change a tiny bit, as in instead of being exactly 12 and 12, it could be 13 and 11, 14 and 10. So that changes a tiny bit maybe every year. But keep in mind that theory is going to be still very, very important. And anyway, even for the calculations, we need the theory. If we just see a random formula with random letter, we still need to know what each letter stands for. Then we're going to go through some examples together. And finally, I'm going to have you practice with some exam questions from previous years. So you can really get an idea of what has been asked. And keep in mind that, especially when it comes to the statistic courses, the questions are basically always the same. They just change the name of the people involved in the example and the numbers. But that aside, it's really a copy paste to the next year. And one last thing, so you might have noticed there's also a WhatsApp group. You received an email with the link to this WhatsApp group. And that same email is also very important because there's also a link to a Google Drive folder where the presentation slides are or will be soon uploaded. So, pretty handy. Make sure you have that email. And to join the WhatsApp group, otherwise, you can also scan the QR code on the slide. And there you can ask any questions after today's session if something is still not clear, if you encountered a similar kind of question to what we saw today and you don't really know how exactly would have been done. I'm more than happy to try and answer. And also, if you have any practical questions, say you cannot find the email with the link to the Google Drive, you can ask there and someone will definitely help you out. Okay, now before we begin, just to make sure we all know this more practical information about the exam, I'm sure you already know this, but you're gonna have 24 multiple choice question with 4 answer option, and more or less consider that a third of them, so 8 out of 24, will be purely theoretical question. So unfortunately, there's no saving there. It's just about studying and remembering the theory. Then other 8 will be purely statistical. So you have the formula, they give you the numbers, you put them in the formula, you calculate. That's it. The last 8 are somehow a bit more complicated because they are a mix of theory and statistics. So it's not as easy as, okay, I take the formula, I put the numbers, that's it. but it's also not only theoretical. So there's probably going to be some steps in between that you need to do in order to arrive at whatever formula, or you have to play a bit around with the formula. So you need to know the theory behind it really well. And then based on those concepts, you eventually do some calculations. So this is why I say that it might change in terms of not being like 12 theory and 12 statistical, but it might be 14 and 10, because these last 8, sometimes they're more theory than statistics, other time they're more statistic than theory. How do you pass? Well, hopefully you aim for something better, but to pass, you will need at least 15 correct answers. You have 180 minutes, and the exam is going to be on Tuesday, the 16th. Now, you have 24 questions, 180 minutes. So I really, really advise you to take your time. There's no rush. And the calculation, again, they're not that many. So worst case scenario, they're like 12 out of 24. So, and 180 minutes, it's a lot for those. So really take your time, double check, because a lot of the times, and I've done those mistakes myself, the only thing you do wrong is copying the wrong number in the calculator. So make sure that you do everything slowly and correct. Okay, so moving on. Now, just to give you an idea, this is an exam analysis based on 3 exams that have been administered in the previous years. So here you can see more or less what kind of topics were asked. So how many questions were asked for each one of these topics. So for example, you might notice that Cohen's kappa is something that, yes, it was always asked, but only one question. Well, if we look at the estimation methods, there were always at least 2, but sometimes even 4 questions about it. So you can get an idea of which topics are also more important to focus on, especially if you're close to the exam, you don't have much time left, and you want to do a very quick recap. Then you can have a look specifically into each one of the 3 exams. These are on the slide, so if you like graphs, be my guest. Okay, so what are you going to need for today? Pen, paper, and the calculator, because we are going to go through some calculating questions, because those are maybe the most complicated. Theory, in the end, you just have to know it. But the calculation, especially if you've never seen an example on how it should be done, those can be tricky. Now, this is an example. So we're not going to answer it now, but it's just to give you an idea. And by the end of today's session, we're going to come back to it, and you should be able to answer it. Okay, so what kind of calculations might you find at the exam? I'll just very, very quickly read it, and then we move on. A researcher wants to develop a selection test to select the 20% most skilled students. He assesses the quality of the items by looking at the association with the dichotomized RES score. Based on a sample of 5 students, he wants to determine the phi coefficient of every item. Below, you find both the item score as well as the RES score of item 3 for all 5 respondents. For this item, the phi coefficient will be estimated to be... Now, let's put this on pause. Keep it in mind. We're going to come back after today's session once we go through all the theory and especially understanding what all these things are. What is the dichotomized RES score? What is the phi coefficient? And so on. Okay, now, it's a calculation. I get that it can be scared. So theory, it's what you have in everything. But hopefully by the end of today's session, after we go through everything together, we see some examples, you're going to be able to answer it. And this is one of those that maybe it's not as straightforward of a calculation, but there's a little bit of steps that you need to do in between. So there's also some understanding there. Don't worry. I'm sure that after today, you're going to be able to answer it. Okay, so now before we actually start the training, just wanted to say that we have 2.5 hours today together. Obviously, it's not full training. Because it's 2.5 hours, I would usually do 2 breaks. So we would go on for around 45 minutes, have a break, other 45 minutes, have a second break, and then the last 45 minutes. The 2 breaks can be of either 5 or 10 minutes. I'm going to ask in the moment, whatever you prefer. and majority wins. If you're exactly split, which happens a lot of the times, I'm gonna do 7. Okay, and if you have any questions at any point, please feel free to mute yourself, raise your hand, or write it in the chat. Obviously, if you write it in the chat, it might take me a bit longer to answer you. And any feedback, if I'm going too fast, too slow, those are also always appreciated. Okay, so the content of today is mainly going to be reliability. So you might have noticed that this is a big topic by the amount of lectures that were about it. The other big topic is validity, but especially reliability is a lot for this course. So we're going to first define it, so what it is, and especially what it is within the classical test theory. Then we're going to move on to the methods overview. So all those methods that we can use to estimate the reliability. And finally, we're going to talk about item discrimination. So how do we find out if an item is doing good or bad? So should we keep this item because it's serving its purpose, so it's good for the reliability? Or should we maybe delete it because it's a bad item and it's lowering the reliability? Okay. Now, first of all, what is reliability? Now, reliability is defined as the degree to which test scores vary when the test is administered at least twice under equal condition to the same person. So basically, it's about how reliable I am in my measurement. So the accuracy of measurement. How accurate am I in measuring that same thing? Because if it's the same person in the same condition, supposedly I should be able to get the same exact measurement. So it's about the variation, and we're going to see reliability when there's no variation there. Now, according to classical test theory, reliability is based on 3 things: observed score, true scores, and measurement errors. Now, the values that we obtain through research and testing are the observed score, so the test scores. If I take a test about intelligence, like the IQ test, the score that I get at the end, my IQ, that's the observed score, the test score. Then we have the true scores, which are the actual score, so my real intelligence. Independently of the specific test that I took, I'm always going to be that intelligent. Finally, though, we have to say that these true scores are difficult to determine. So a lot of the times, we're going to see that the observed score is not the same as the true score. So my true intelligence might not be exactly the same as the intelligence I obtain once I take the IQ test. How come? Well, because there's always going to be some measurement error. So that error biases my result, let's say. And that's why we're basically never going to be able to make a good estimate of the true score. So my observed score will not be exactly the same as the true because of some measurement error. Now, this is the most fundamental thing to remember. This is what classical test theory says, that X, meaning the observed score, the test scores, equal the true scores plus the error. So they equal a systematic part and random influences. Systematic part, and that's the true score, it's because they don't vary. So it doesn't matter what test I'm taking, at what point of my life, my intelligence is that, my true actual intelligence. And then there's random influence, meaning the error, meaning that it's completely random. So if I take the same test now and then in a week, the error will be different. It's completely random. Okay, so you see, if there were no error, then our observed score would be the same as the true. But a lot of the times there is the error. And this is why there's a difference between what I actually observe and what I should see. So how is then the reliability calculated? Well, the reliability will be the result of taking the variance of the true scores divided by the variance of the observed score. So the variance of the test scores. Now, another thing that we can notice from the formula is keeping in mind this fundamental equation. This also applies to the variances, meaning that the variance of the observed score is equal to the variance of the true scores plus the variance of the error. So we could rewrite this formula as variance of the true divided by variance of the true plus variance of the error. So we are dividing something by itself plus error. Hence, this is why I say that if the error is not there, so we do variance of the true divided by variance of the true plus 0, because there is no error, I'm basically dividing something by itself. Variance of the true divided by variance of the true. So we get 1. And this would be the ideal situation. The reliability can go from 0 to 1. The closer to 1, the better. 1 would mean perfect reliability. So we are actually perfectly able to measure the true scores because there's no error. So the observed ones are exactly the true. Perfect, ideal, imaginary word and situation. But keep in mind, if the error is 0, the reliability is 1. And this is a very, very typical theory statement that you get at the exam. They tell you if the error is 0, then the reliability is 1, or then the reliability is 0. If the error is 0, reliability is 1. This is a very typical statement. So they play a bit around on these things. And this is just to give an indication of what would be considered good, what would be considered bad reliability. Overall, keep in mind that the biggest distinction that they make is between individual and group level. So you see that at the individual, we want stricter criterion, while when it comes to the group level, even a bit lower reliability, it's still fine. So a lot of the times it depends on the purpose that we have in mind whenever we administer a test. Now, one important concept that we want to mention is the standard error of measurement, which it's basically as if we were to say the standard deviation of the error. Now, the standard error of measurement can be calculated with this formula that we see here. What is the formula? Well, we have the standard deviation of the observed score, so the test score, times square root of 1 minus the reliability. And the variance of the measurement error indicates how spread it is, so how big the measurement error is. And obviously a high value then indicates that we have a weak measurement that contains a lot of measurement error. So also in the end, pretty shitty reliability. So reliability and error, they go in opposite direction. So the higher the reliability, the lower the error. The higher the error, the lower the reliability. Then one last thing that's important to know, and also to keep in mind that it's influenced by the standard measurement error, is the confidence interval. For example, in this course, you're mainly going to talk about the 95% confidence interval, but if you remember maybe from introduction to statistics, you could also have 90% confidence interval and so on. Okay, so the 95% confidence interval, it's an interval, so it's going to have a lower limit and an upper limit. So this is why you see that the same formula there is only different with a minus and a plus. So for the lower limit, we're going to have to take the score of a specific person minus 1.96 times the standard error of measurement. For the upper limit, the same, but with the plus. Okay, so basically what we see then is that the confidence interval depends on the standard error of measurement. So the greater the measurement error, so the more error we have, the wider the confidence interval. And the wider the confidence interval are, then the less accurate we are in the interpretation. So more error means larger confidence interval, which means we are less accurate in our measurement. And that's not something we want. So also here, if we have very little error, then we have very tiny confidence interval, which means that we can be pretty sure, like, okay, the true scores are actually in this very tiny interval. And that's good. That's what we hopefully want to see. Okay. Now let's see a kind of exam questions about this together. So I'm just gonna very quickly read them, and then what I do is that I leave you some time to try and answer it, and you please let me know whenever you're done. So you can either type done in the chat, you can directly message me the answer, or you can use whatever emoji reaction you want, a cat, a heart, doesn't matter. Just give me a sign that we can move on. And even if you have no idea what to do, or it's just too early in the morning to activate your brain, that's also fine. Just give me a sign that we can continue. Okay, so on an exam, James has a test score of 5, Rick has a test score of 7.5, and Max has a test score of 8.5. The standard deviation of the test score is 2, and the reliability is 0.89. Which of the 95% confidence intervals overlap? And this is an exam question that I've seen in every single exam. What happens is that James turns into John, maybe, and Max turns into Steve. And the numbers are not 5, 7.5, and 8.5, but 6, 3, and 8. So every single time it's there, they just change names and numbers. So it's pretty important that you understand how to do this one. So try and let me know when we can have a look at the process. I got some reactions. I'm gonna wait just a tiny bit more for the others, and then we can continue. Okay, so I would say we have a look at it, and I got a very good question in the chat. So I'm gonna answer that as we go through the explanation. Okay, so as you all said, it is indeed answer option C. So the intervals of James and Rick overlap, and the intervals of Rick and Max overlap. Okay, so how do we get there? Now, before you jump on to the answer and the calculation, I always advise to try an understanding what is going on, what you have, and what you need. First of all, 95% confidence interval. So what do we need? These formulas here. Lower limit, upper limit confidence interval, and you're gonna do this for each one of the three people and then see which ones overlap. Okay, then what do we have? They give us the standard deviation of the test score, so the observed score, and then the reliability. Okay, do we have everything we need? No. So we need the standard error of measurement, but we don't have that. We can calculate it though. How? Well, by using exactly what they're giving us. So we're gonna put 2 in the formula times the square root of 1 minus the reliability, which is 0.89. Once we've done that, we have the standard error of measurement. Now we can move on and calculate the confidence interval. So a typical mistake that gets done here is that maybe some people use the standard deviation here instead of the standard error of measurement. So this one wouldn't be considered as purely statistical, but more the in between, because indeed there's also the understanding that you need the standard error of measurement, finding the formula, calculating it, then calculating the confidence intervals, and then also understanding which ones overlap, which don't. So once we have that, what do? Well, we're simply going to calculate the confidence interval for each person. So we're going to take the score of each person and put it into these formulas. So James had a score of 5, so we do first 5 minus 1.96 times the standard error of measurement, which we just calculated to be 0.66, and then the same thing, but with the plus. Once we do that, we have James' confidence interval, which goes from 3.71 to 6.29. Okay, we're gonna do the same exact thing for Rick, but putting his score, which is 7.5. Now we find out that his confidence interval goes from 6.21 to 8.79. So if we look at James, he went up to 6.29. Rick starts at 6.21. Very close, but there is that tiny bit of overlap. So from 6.21 to 6.29, those two confidence intervals overlap. What about Max? Max had a score of 8.5, so we put that one in, and then we see his confidence interval from 7.21 to 9.79. Let's see. James and Max, do they overlap? No. One finishes at 6, the other starts at 7. So definitely no. What about Rick? Well, Rick finishes at 8.79. Max starts at 7.21. So they overlap, and even for quite a bit. So in the end, we have James and Rick, and then Rick and Max. So answer option C. That's it. So remember, there's that one step in between that we need to do. So let's not jump onto the calculation, but let's first think, what do I have? What do I need? Okay, is it clear for everyone? I'm gonna assume you're all yesing with your head. Okay, perfect. Then let's continue. Now, moving on to the estimation methods. So all these would be the ideal situation in which we can estimate the reliability just like that. But if you remember, I told you that to calculate the reliability, we would need the variance of the true score and then divided by the variance of the observed score. Now, why would be administering tests to basically obtain the test score, which is a sort of estimate of the true score, if we already knew the true scores? That wouldn't really make sense. So in real life, obviously, we don't know the true score. Basically, kind of like everything we have in psychology, we don't know. Like intelligence, depression, we don't just walk around the street, look at people and be like, oh, I see your true level of depression. That's not how it works. So how do we estimate the reliability then? If for estimating the reliability, we need something that we cannot know and we're literally using tests to estimate, well, there's going to be also some method to estimate the reliability because we don't know the true scores. And there's these three big categories: the test-retest method, the parallel forms method, and then the internal consistency method. And the last one that we see here, the internal consistency methods, it's actually comprehending 4 different types. So test-retest method, parallel forms method, and then 4 different types of internal consistency methods. Okay, so what are the differences that we already see here? Well, for the test-retest method, we see that we're gonna require 2 test administration. Specifically, same test, but administered twice. So I'm gonna take an intelligence test now, and then in a week. And the comparison will be between the score I got now and the score I got in a week. So we compare scores on the same test that's being administered twice. And that's why test-retest method. So I test and then I retest. Otherwise, we can have the parallel forms method. Again, we need 2 test administration, but this time, this test will be different. So it's not same test given twice, but it's 2 different tests, and I compare the scores on these 2 different tests. But yes, they are different, but they are parallel. And we're gonna see exactly what it means for them to be parallel. But long story short, it's kind of like saying it's not really the same test, but they're basically equal. So they should be very, very similar and measuring the same thing, but not exactly the same test. So pretty complicated to actually have in real life. But keep in mind, they should be parallel. And we'll see how do we check if they're parallel. And the last method is the internal consistency methods, which I told you it's actually a category that comprehend 4 different specific types of methods. But the thing that all these 4 methods have in common, and this is why they all belong to the internal consistency methods, is that we're going to administer just one test once. So this is already a big difference compared to the other. It's pretty handy. I just give one test to one person, one time, and that's it. And I'm going to compare the scores on parts of the test. These parts might be I compare the first 10 question with the other 10 question. Or maybe I just compare each single item. We don't know yet. So we're gonna just compare the little items of my test. So I'm kind of acting as if my test that's made of 24 items, like the test theory exam, instead of being 24 items from the same test, it's as if each item was a test by itself. And I compare those. Okay, so basically what I check is the internal consistency. So how consistent with each other are the items within my test? So how similar? Do they all measure intelligence, if it's a test about intelligence? Okay, let's have a look at the first one. the test-retest method. Now, as I said, we are just testing the same thing, so we are administering the same test under exactly the same condition twice. So I take it now and then I take it again in a year. One very important thing to say is that there is a fundamental assumption, and this assumption is that the two replications are independent. Meaning, for example, that there's no memory effects. What does it mean? If I take an intelligence test now, and then I take it in a week, but I don't really answer the question because I did all the calculations, I thought about the problem, and that's it. But the second time, I just answer because I go like, let me see. Okay, a week ago, oh yeah, I remember question 1 was A, so I'm gonna put A. Question 2 was C. Okay, so C. Question 3, C again, so C. That's not good. That would be a memory effect. So I'm answering only because I remember what I answered the first time. That's not what should happen. These replications should be independent. So I should still answer because I actually do all the thinking, all the calculations, and I think that the correct answer is that one. So very important, these replications have to be independent. Okay, and we'll see what happens if that's not the case. So how do we estimate the reliability? Simply with the correlation. So we calculate the correlation between the test score on the first application of the test and the test score on the second replication. So I have the test score of the test that is being taken now, and then the test score after a week that the people retake the test. I simply do the correlation between these test scores. And the correlation is calculated with that very long, annoying process. So the fact that we need the covariance and the two standard deviation. So you're gonna want to first obtain the means, the deviations from the mean, square deviation, then the variance, standard deviation, and so on. So all those little steps that you might remember from lecture 1. Okay, and that correlation is gonna be the estimate of the reliability. That's it. So for the test-retest method, the correlation between the scores in the two test applications are the estimate of the reliability. Now, if we are using a test-retest method, but the replications are not independent, and this is very important because this is such a typical theory question at the exam. So they might tell you, if I use the test-retest method, but the replications are not independent, I will risk overestimating the real or the true reliability. True or false? Okay, so are we underestimating or overestimating? So basically, if I use this method, but I violate the assumption, so I literally know that the replication must be independent, but actually they're not, but I still use this method, what happens? Am I overestimating or underestimating the reliability? So is this correlation actually higher than the true reliability or lower than the true reliability? Well, both. So both are fine. So if at the exam they say underestimation, true. If they say overestimation, true. If they say higher than the real, true. Lower than the real, true. For the test-retest method, if I use it, but the replications are not independent, I could be either overestimating or underestimating. So both can be true. So very important to keep in mind, both overestimation or underestimation are fine. So both higher than the actual reliability or lower than the actual reliability. Okay, so this is very important to keep in mind for the exam. Now the parallel forms method. This is the second method, and I told you that parallel sort of means that the tests are very similar, but they're not exactly the same one. And to check if the tests are parallel, there's two criteria, two assumptions that needs to be satisfied. First of all, the fact that my true score while taking the first test is the same as my true score in the second test. Why? Well, because I told you that the true score is a systematic part, so it doesn't vary. It doesn't matter what test I take, the true score is always going to be the same. And the second assumption is that the variance of the errors in the first test is the same as the variance of the error in the second. If these two conditions are satisfied, this test is parallel, and we can just use the parallel forms method, and we get a good and accurate estimation of the reliability. How do we obtain this estimate? The same as before. So we're just going to do the correlation between the scores on the first and the scores on the second test. So correlation formula, covariance divided by the two standard deviation multiplied. That's the estimate of the reliability. And one other thing too to say, also for the parallel forms method, we are assuming that the replications are independent. So also here, again, if the replications are not independent, then the estimate of the reliability might be either too high or too low. So either overestimating or underestimating. Now, there's a couple of problems. First of all, as I told you, it's hard to construct because we basically have to have the same test, but different at the same time. And especially one problem here is the criterion 1. Okay, so why are we using the parallel forms method? Well, we are using it because we don't know the true scores. So we cannot calculate the reliability with the true score. So we're trying to estimate in an alternative way. But then the estimation method, so that we don't use the true score, as one of the assumptions talks about the true score. How is that possible? So it's a loop. To not talk about the true score, we use a method that in order to be used accurately needs to check the true scores. That's not possible. So what can we do? Well, we could empirically verify if they're parallel. So we don't throw this method in the bin, but there's an alternative practical way that we can actually use to check if they're parallel. And these are the 3 criteria. First of all, we are going to check that the mean of the test scores in the first test is the same as the mean of the test score in the second test. This one we can check. Then we're going to check that the variance of the test score in the first test is the same as the variance of the test score in the second. And the last thing, we're going to check the correlation between the test score on the first test and another third test that we're not really interested in, and see if that's equal to the correlation of the score on the second test with that same other test that we're not really interested in. If these conditions are satisfied, then we know that the 2 tests are parallel, and we're good to go. Otherwise, what if we find out that the tests are not parallel? What happens? Well, if the tests are not parallels, the estimate of the reliability, so the correlation between these 2 tests, these 2 non-parallel tests, will be lower than the true reliability. So we're going to be underestimating the true reliability. So this is important to keep in mind. Here, it's not both lower and higher, only lower. So at the exam, let's say they say the parallel forms method was used, but the tests were not parallel. So we are underestimating the true reliability. This is true. So the estimate, if they're not parallel, will be an underestimation. So basically, this correlation will be lower than the real reliability. So for test-retest method, if they were not independent, either underestimation or over, either lower or higher. For parallel forms, if they're not parallel, underestimation. So lower than the real, than the actual reliability. Okay, is this clear? Because these are the very, very typical theory questions. So you will see that the statements say these little things. Okay. I would say we have our first break and then we're going to continue with the last, which is actually a category of 4. So, would you want 5 or 10 minutes at the moment? You can either type it in the chat or unmute yourself, and majority wins. I see 5, 5, 5. Okay, then let's do 5 minutes. So let's meet again at 9 and 54 minutes. Okay, so it's 9:54. If you're back, please let me know and then we can continue. Okay, I see some reactions. Good. Okay, and if you have any questions at any points, absolutely ask. Okay, I would say we continue. Okay, so the last one of the estimation method, which is actually a category of 4 different types of methods, is the internal consistency method. Now here we're only using one test, and we are dealing with the interrelationship between parts of this test. So basically, how are the items or part of the test connected with each other? And this method is mainly used with composite scores. Oh my god, so scary. What is a composite score? Kind of like any single test score. So the test theory exam final points that you get, that's a composite score. So the fact that each item gives me a score, like for example, a 1 if I got it correctly, a 0 if I didn't. To get the total score, the composite score, I just sum up the scores in each item. So first item I got correct, 1. Second wrong, 0. Third correct, 2. Okay, so I'm a 2, and so on. So in the end, the fact that you get 19 out of 24 for the test theory exam, then 19 is a composite score. Long story short. And the fundamental idea of this method is that different questions, so different items, can be seen as separate tests, basically. And then I compare these separate tests with each other. Now, one part of a test can be either a test half, and that would mean split half method. So we are taking the test, we're dividing it into 2 equal halves, and then we are comparing these 2 halves with each other. Or it could also be the individual items. And that would mean either the row Cronbach's alpha, standardized Cronbach alpha, or the KR20, the Kuder-Richardson 20. Either one of these. We will see why and when I would pick one instead of the other of these 3. But keep in mind, the first one is comparing 2 halves. The others compare all the items with each other, as if they were all individual tests. Now, if these different parts of the test are all positively correlated with each other, then probably the reliability will also be high. Because one fundamental thing about all the internal consistency method is that we are assuming unidimensionality. What does it mean? It means that we assume that all the items are measuring the same dimension, the same construct. So if I'm giving a test about intelligence, supposedly all my items should be measuring intelligence. But if it turns out that some items actually measure neuroticism, then the test is not unidimensional, but it's multi-dimensional because it's measuring multiple things, multiple construct, intelligence and neuroticism. So what happened though if I use one of these tests, but then it turns out that my test about intelligence actually also measures neuroticism? So it's not unidimensional, but it's multidimensional. Well, if that's the case, we are gonna underestimate the true reliability. So our estimate will be lower than the real one. This is also important. If I use an internal consistency method, but the test is either not unidimensional or multi-dimensional, this is how they might formulate it, then I'm going to risk underestimating the true reliability. Or my estimate will be lower than the true one. And for this kind of statement, theory statement, they could either say, if I use an internal consistency method and it's multidimensional, blah, 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 or they might specifically say either of these 4 tests. That's fine. Still, keep in mind, any of the internal consistency methods, so split half method, row Cronbach's alpha, standardized alpha, Kuder-Richardson 20, for all of them because we assume unidimensionality. If that's not the case, so the test is multidimensional, we are measuring multiple constructs, then we are gonna underestimate the true reliability. Okay, let's start with the first one. Now the first one is the split half method. So as I told you, pretty straightforward. As the name says, we're gonna divide a test into two equal halves. Let's think about the test theory exam. You have 24 questions. Okay, we're gonna take the first 12 questions and then the other 12 questions. Two equal halves. Then we're gonna calculate the test score for each one of these halves. Once we have that, we're just gonna do correlation between these two halves. Correlation between one half and the other. But, and this is very important, that's not enough. So that's not it. So while before, for the test-retest and the parallel forms, we were calculating the correlation and then we were stopping, so that was enough. Here, there's one more thing that needs to be done. So once we have the correlation between the two halves, we're gonna have to apply the split half Sperman-Brown formula, which basically is just, once we have that half correlation, we put it here, and that's it. So 2 times the correlation of the two halves divided by 1 plus the correlation of the two halves. And this is the estimate of the reliability. So very important, the correlation between the two halves is not the estimation for the split half method, but once we have that, we put it into the split half Sperman-Brown formula. Okay. And one last thing to be said, an important assumption is that for the split half method, we are assuming that the items are parallel. What does it mean? Well, it means that if we use the split half method, but the items are not parallel, then if you remember, just like we said before, we're gonna risk underestimating the reliability. So we're gonna get a lower estimate than the real one. So if I use split half method, but the items are not parallel, underestimation. So lower than the real one. Okay, let's see a more practical exam question. What might I ask you? A researcher makes use of the split half method for estimating the reliability of a test. The test is split into two parallel test halves, which each consist of 25 items. Based on the analysis, a correlation of 0.72 is found between the two test halves. What will be the estimate of the reliability for the entire test? So again, take your time, try and answer, and let me know whenever we can move on to the explanation. Okay, I think we can have a look. So this is the purely statistical one. Why? Because we have a formula and we just need to literally copy what is given to us in the formula. Now, the only tricky thing here is that we need to remember that for the split half method, the correlation between the two halves is not the answer, but there is the formula that we need to apply. And that's important because you will see that if you get such a question at the exam, one of the answer option was actually the correlation between the two test halves. So if you notice, answer option B was that one. So they try and trick you to make sure that you know that the split half method is one step further than the test retest and the parallel forms. Okay, so correct answer was A. A lot of you got it correct perfectly. How do we get there? Well, we need, yes, the correlation between the halves, and usually that will be given to you. And then you just plug it into the Sperman-Brown formula. That's it. Make sure you copy everything correctly in the calculator, because that's literally the only mistake that can be done here. Make sure here there is a multiplication, while below is just a sum. Once you do that, you should obtain the correct answer option. Okay, perfect. Let's continue. Now let's move on to the more complicated ones. First of all, the row Chrombox alpha. Now the row Chrombox alpha, it's kind of hard because it's not so clear what exactly the formula means. So I really want you to understand the reasoning behind it. So don't focus so much on all the different letters that are there, but understand what exactly you need to do. First of all, this is the row Chrombox alpha. There's two Chrombox alpha, row and standardized. What is the difference? Well, the row alpha looks at the row relationship between items, meaning the covariance, while the standardized alpha works with standardized scores, so it looks at the correlation, because you might remember that the correlation is basically the standardized version of the covariance. Why? Well, because the correlation, we know that always goes from -1 to +1, and 0 means no relationship, -1 the strongest but negative, +1 the strongest but positive. And it's always the case. So it's very easy. If I get a correlation of 0.7, I know exactly that that's a positive, quite strong one. But when it comes to the covariance, it's not standardized, it's raw. So I might obtain a covariance of -3227.33. Is that strong? Is that not? We don't know. So it's not that easy to interpret. Okay, now row Chrombox alpha. What do we see here? There's actually two different versions of the same formula. So you can use either one of these two. You get the same exact result. My advice, if you remember both of them and you understand them, given that you have a lot of time, if you do get a calculating question about the row Chrombox alpha, you could always do both of these and check. If you get the same number, you're 100% sure that you have the correct answer. Well, if you get different numbers, then maybe something is going wrong, but only if you really remember them both. Okay, so let's see what is going on. First of all, the first part is the same for both the version. So k divided by k minus 1. What is k? K is the amount of items that we have in our test. Test theory exam, 24 questions, 24 items. K would be 24. That's it. Then, in the first version of the formula, what we want to do, and keep in mind, because we work with the covariance, we're actually gonna make use of one of the matrix. If you remember one of the first lectures, the professor mentioned that there's two important matrix tables, very handy. Those are the variance-covariance matrix and the correlation matrix. For the row Chrombox alpha, we're interested in the variance-covariance matrix. What does that matrix look like? Well, in the diagonal, we're gonna have all the variances of diagonal, so all the other numbers are gonna be the covariances. Okay. So what we do, we make use of the table, and at the numerator here, we're gonna sum up all the off-diagonal numbers, meaning all the covariances. So we want to sum up all the covariances from the variance-covariance matrix, so all the numbers that are not in the diagonal, and then divide by everything. So every single number that we see in the variance-covariance matrix. That's it. So basically, the sum that we did here, plus also the numbers on the diagonal. Otherwise, the other version of the formula, we would do in brackets, and that's very important, 1 minus, at the numerator, summing up only the diagonal numbers, so only the variances. We only sum up the variances, the numbers on the diagonal, divided by all the numbers. That's it. Now, one important thing for the theory question is, when are we overestimating? Where are we underestimating? Well, here we make a very important distinction between whenever we talk about the population and whenever we talk about samples. And this is very, very important because you will see literally that at the exam they specify if I'm applying the rho Chrome Max alpha or if I'm using the rho Chrome Max alpha in a population, my alpha will be da-da-da-da. So it's very important. You need to very carefully read if they say in population or in samples, because the answer changes. In population, the alpha will always be either equal or lower than the true reliability. So either the same or an underestimation. Well, in the sample, the alpha varies. So it could be anything. It could be lower, it could be the same, it could be higher. It could be anything. So it could be an underestimation or an overestimation. But this is very important because a lot of the times, exam, the theory statement says in population, the alpha is an overestimation. False. But a lot of people maybe say true because they remember that the alpha vary. No. In the samples, in the population, only under or the same. Population, underestimation or the same, so lower or the same. In samples, under, over, the same, lower, higher, the same. It varies. Okay. Now let's see the standardized Cronbach alpha, and then we're gonna see a calculating exam question. The standardized Cronbach alpha, as I already mentioned, works with standardized score, so we talk about the correlation between the items. So what kind of matrix are we gonna use? The correlation matrix. What does the correlation matrix look like? Well, it's very easy to find out because on the diagonal, we're gonna see all ones. So on the diagonal, it's all ones. And then off diagonal, there's the correlations. Okay. Now, the formula that we see here can be difficult to comprehend, but in reality, it's pretty straightforward. So this is the formula for estimating the reliability. We see K. K is still the amount of items. I have the 24 question of the test theory exam. K is 24. What about this one? Now, you might remember that we already saw sometimes letters like X with a line on top. And what was that? Well, that meant that we are talking about the mean. So what they're saying here is basically just do the mean of all the correlations. So what we have to do is sum up all the correlations and then divide by n, so the amount of correlation that we summed. So let's say I have 3 people that took a test. The first person got an 8, the second got a 7, and the third also got a 7. How do I do the mean? Well, I'm going to do 8 plus 7 divided by 3. So the amount of scores that I summed up. Same thing here. I sum up 20 correlations, then I divide by 20. That's it. And this is basically what this fancier version of what I just says. So it's telling you sum up all the correlations and then divide by basically how many you summed up. So pretty straightforward. I summed out 20 correlation, I divide by 20. So I sum up all the off-diagonal numbers because those are the correlation. So very important, do not sum up the ones, only the actual numbers. And then divide by all those cells in the table. Now, important distinction. Why would we decide to go for the standardized or the row Cronbach alpha? Obviously, for the exam, if they give you the correlation matrix, you do the standardized Cronbach alpha. If they give you the variance covariance matrix, you do the row standard alpha. Okay, but in real life, why would I go for one or the other? And this is important for theory exam question. Why would I pick this one instead of the other? Well, we're going to use the standardized Cronbach alpha whenever the items differ a lot in variance, but not in relevance. What does it mean? Okay, straightforward example. Sometimes in an exam, you might have some exam questions that are true or false. So you only have two options. The variance is literally just two. Or you might get four answer option, A, B, C, and D. And then the variance is four. So in one, you only have two options. So like you have the 50-50. While in the other, you have four. So you see the variance is different. But in the end, both of these questions will give you 1 point if you get it correct. So if you get this one correct, you get 1 point. If you get this one correct, you also just get 1 point. You don't get one and then 2 points. You get one for both of them. So in terms of relevance, doesn't matter. They all give you exactly the same score in the end. So you see, they differ in variance, but not in relevance. If this is the case, we would prefer the standardized Cronbach alpha. Otherwise, we could use the row Cronbach alpha. Okay. Let's see an exam question. Now, both the covariance matrix up and the correlation matrix down of a 7-item test are given on the left. Calculate the standardized Cronbach alpha. Now, at the exam, what might happen is that they either give you just the one table that you need and that's it. They might give them both. They might not specify the alpha, but then give you one specific matrix, and then based on the matrix that they give you, you should know which one to use. Or yeah, they might try like and trick you also in this tiny little way. Or they might give them both, but then specifically say which one is what. So that's just an exercise for you. Make sure that you know which matrix is what and which one you need for each one of the alphas. Okay, so try and let me know whenever we can move on to the explanation on how to calculate the standardized Cronbach alpha. I'm gonna wait 1 more minute for the others to also give me a sign, and then we can move on. Okay, I would say we can start having a look. So first of all, the first thing to do is understand which matrix we need. Now, they ask us to calculate the standardized Cronbach alpha, meaning that we work with standardized scores, so we want the correlations, meaning correlation matrix. Now, in this case, they say that it's this one. If they didn't, how do we understand that this is the correlation? Well, because in the diagonal, we see all ones. Okay, now correct answer was C, 0.65, but how do we get there? Okay, so this is the matrix that we need. Now, before jumping onto the formula for the reliability, we need to find out that kind of like R with the line on top. Either you remember by R this sort of formula, or the concept is that we need to do the mean of the correlations. Basically, we're going to sum up all the correlations and then divide by the amount of correlation we summed up. So we're going to do 0.45 plus 0.35 plus 0 plus 0 plus 0 plus 0 plus 0.25. So all the green numbers, those are all the correlation. They all need to be summed up. And then we divide by the amount of cells that were here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And you might have realized this is just a mirror. So if there's 21 here, there's also 21 here. So 42. So you either sum up all the green numbers and divide, in this case, by 42, or if you want to make it faster, you can also just focus on half of the table. So you only sum up these half, but then divide by 21, obviously, because then you're only summing up these 21 numbers. So that's up to you, whatever you want. Either all the correlations and then divide by all those correlations, or just half of it. It doesn't matter. You will get the same result. Otherwise, what is this formula officially saying? But it's not in the formula sheet, so that's why I tell you, just keep in mind that you want to do the mean of the correlation. So summing up all the correlations, not the ones, and then dividing by n, the amount of correlations that you summed up, which was either 42 or 21 if you only looked at half. Obviously, also this number would be halved. If you only do half of the table, it's not going to be 8.9, but it's going to be 4.45 divided by 21, or 8.9 divided by 42, whatever you prefer. Otherwise, in terms of this formula, what they say, sum up all the correlation, so all the green numbers, and divide by the amount of items times the amount of items minus 1. So basically, 7 times 6. How much is 7 times 6? 42. So exactly what we did. Summing up all the green numbers and then divided by all the correlations that we summed up, which were 42. Once we have this, we just put it into the formula. So K is the amount of items. We have 7 items, so K is going to be 7 times the mean of the correlation that we just calculated, and then divide it by this. Okay, is this clearer now? Okay, good. Perfect. Now, let's assume for a moment that instead of this, at the exam, they ask you to calculate the rho max alpha. How would you have done it? So I'm again going to give you a bit of time, and I want you now to calculate the rho max alpha. So make sure you pick the right matrix, and then just apply the formulas. So I'm going to again give you some time, and please let me know whenever you're done with your calculations. Because yeah, the exam, it's very typical. They either ask you to calculate the raw Cronbach alpha or to calculate the standardized Cronbach alpha. And then maybe they ask you a theory question about the other one. I'm going to wait 1 more minute, and then we're going to move on to the answer. Okay, so let's have a look. Now, rho Cronbach's alpha, so we're working with rho relationship, meaning the covariance. So we're going to need the variance covariance matrix, which is going to be the one here on top. Now, what do we see? Well, in the diagonal, we're going to have the variances of diagonal covariances. So the blue numbers are the variances, the green numbers are the covariances. Okay, now how is the rho Cronbach's alpha calculated? Well, there's those two formulas, so it's up to you which one you prefer. If you want to be 100% sure, you can try them both, but only if you know very well how to use them. Okay, so this was the first option, and this was the second option. Okay, now, how do these look like? Well, the first bit is the same for everyone. So for both of them, we want to take the amount of items, which is 7. K is 7. K is the amount of items, divided by 7 minus 1. Okay, and that's the same for both the formulas. So I wrote them both here. Then, for the first formula, they say multiply by the sum of the off-diagonal elements, meaning the covariances. So we're going to sum up all the green numbers. So 14.8 is the sum of all the green numbers here, divided by everything. So to these 14.8, we are going to add the blue ones. So every single number that we see in this table. That's it. Otherwise, the other version of the formula, very important to put the brackets, 1 minus the sum of the diagonal elements, so the variances, the blue numbers, divided by everything. So to the blue numbers, we also add the green ones. That's it. If you do it correctly for both of these formulas, you should obtain, more or less, depending on rounding, 0.76. So it's up to you which one you want to use. If you remember them both, but very important, know them both correctly. You can always try them both because there's a lot of time. And if you get the same number, you're 101% sure that you did everything correctly. Okay, is this clear? Are there any questions? Okay, perfect. Then I would say before we move on to the last internal consistency method, which is here the KR or Kuder-Richardson 20, we can have our second break. So once again, would you want 5 or 10 minutes at this moment? So I see 5. 5 again. Okay, then we're gonna do 5 minutes. So let's meet again at 10 and 41 minutes. Okay, so it's 10 and 41 minutes. So if you're back, well, if you want to turn on the camera for this last part together, you're more than welcome to. Otherwise, just give me a sign that you're still here. Okay, good. I see a reaction. Perfect. Okay, I would say we continue then. Okay, so the last one of the internal consistency methods to estimate the reliability is the Cuter-Richardson 20, the KR20. Now, when would we use this one instead of the alphas? Now, in real life, kind of never, but officially for dichotomous data. So whenever we have the data that it's like true, false, yes, no, either you get the point or you don't. So the two option, like black and white kind of thing. So if you get it correct, you get a 1. You get it wrong, you get a 0. Okay. Now, the formula is all of these. So the first bit is the same as what we saw for the row Chromebox alpha. So again, K, number of items, we have 7 items, 7 divided by 7 minus 1. Okay. The second bit is 1 minus. The part on top is basically the variance for dichotomous data that we can obtain by doing p-value times the q-value. Now, you might have already heard that p-value in this course, and it's not the p-value that you use in Intro to Statistics to find the significance of a test, but it's a different thing. Yes, they have zero imagination. They decided to call it the same way, but it's a completely different thing. Now, the p-value is basically the proportion of correct answer. So the proportion of people that got the item correctly. So assuming that if you get it correctly, you get a 0. If you get it wrong, if you get it correctly, you get a 1. If you get it wrong, you get a 0. Then we see 7 people out of 10 got the 1. So 7 out of 10, that's the proportion, the p-value. Okay. Q is the opposite. So the proportion of people that got it wrong. So if 7 out of 10 got it, then 3 out of 10 didn't. So the Q value is basically 1 minus P, the remaining proportion. Okay, divided by the variance of the test. Okay. Now, one thing that's important to keep in mind is that the estimate of the reliability that we will obtain with the Cuter-Richardson 20 is going to be exactly the same as if we had calculated the row Chromebox alpha. So we get exactly the same number. And this is why in real life, in research, basically no one is going to use the Cuter-Richardson 20, but everyone will just go for the alpha. But this is something important to keep in mind for the exam, that the estimate will be exactly the same. So say they give you a theory 1, and they tell you, oh, the row alpha was calculated to be 0.76. What would have been the estimate if we had used the Cuter-Richardson 20? The same, 0.76. Or otherwise, they might ask you, why would I prefer the Cuter-Richardson 20? Or in general saying, if we have dichotomous data, the best choice would be to use the standardized Chromebox alpha. No, the best choice would be the Cuter-Richardson 20. So when it comes to this one, usually if you get asked any question about it, it's purely going to be theory-wise. So I don't think it's ever happened that they ask you to calculate the Cuter-Richardson 20 because it's just very long, so extremely time consuming, and no one does it even in real life. So at most, you might get a theory question about this. But just to get an idea, what would be the steps if we had to calculate it? So basically, we're going to break down this formula into little steps. Now, the first thing that we would want to obtain is the test score, X, because we see that here we need the variance of the test scores. So we're going to have to obtain the test score. How do we obtain the test score? We simply, for every person, sum up the score that they got in every item. So the test theory exam, you start counting, okay, how many did I get correct? 19. Okay, that's my test score. That's it. And then we want to obtain the mean. So basically, we're going to sum up all the test scores and then divide by n. That way we obtain the mean. Okay. Then we're going to calculate the deviation score. So the deviation scores from the mean. So I scored 8. The mean is 7. What's my deviation score? 8 minus 7. So the score of each person minus the mean. Then we're going to have to square the deviation score. So if someone has a deviation score of 2, then it becomes 4. Squared deviation score. Once we have all the square deviation score, we're going to do the average of them. So we're going to sum them up and again divide by n. And that is actually the variance. So now we have the variance of the test scores. So this part here, what are we missing? The numerator. How do we obtain that one? Well, we're first of all going to calculate the p-values. And I told you that when it comes to dichotomous data, the p-value is the proportion of correct answer. And when it's dichotomous data, that's basically the same as the average. Because every person on each item either gets a 1 if they got it correct, or they get a 0. So what is the average? Well, the average would be basically summing up ones and zeros. So 1 plus 0 plus 0 plus 1, which eventually gives us, we have 5 people, 2 got it correct, 3 got it wrong. So that's 2 out of 5. What is the mean? Well, 1 plus 1, that's 2, plus 0 plus 0 plus 0, that is 2, divided by 5, 2 out of 5. So you see, they are exactly the same. So when we have dichotomous data, the p-value is exactly the same as the mean of the item. So we do the p-value of each item and the q-value of each item. Q is just 1 minus p. So if we found a p-value of 0.4, Q is just going to be 1 minus 0.4. Okay, and we do this for each item in our test. The last step, calculate the item variances. How? By doing P times Q. So we found out that P was 0.4, Q was 0.6. We just do 0.4 times 0.6. And this is the variance of that specific item. Then we do the same for all the other items. Once we have the item variances, we sum them up. Because back to the formula, it was saying multiply all of them and then sum all of this multiplication up. Last step, we just put everything into the formula. So we know K is the amount of items, and this we just calculated. So you see, it's not that complicated, it's just long. And this is also why at the exam, they're not going to ask it. Because they don't want you to go over extremely long calculations. They want to understand that you got the concept. But they might ask something theoretical, like those things that I mentioned. Okay, now moving on to the last big topic for today, the inter-item correlation. Now, the inter-item correlation provides an insight into the internal consistency. So that thing that we saw before, basically, how consistent are the items with each other? So how well are they measuring that one thing that they're supposed to measure? And developing a good test obviously depends on a lot of things, among which the number of items that we are including in our test, the hypothetical understanding, as in, if I want to measure depression, maybe I'm not going to put an item that says, I do not like dogs. Sure, maybe someone might argue that if you don't like dogs, you're depressed, but that's not necessarily the most stereotypical item to find out if someone is depressed or not. And then test lengthening and test shortening, meaning that if an item is bad, we might want to remove it. Just as if an item is good, we might want to add it to our test. But how do we determine which items we should remove, which one we should retain, in case which one should be added? Well, that depends on item discrimination. And there's a number of indicators that can help us with item discrimination. So item discrimination is basically understanding how well an item is functioning. So how capable an item is in discriminating between, for example, if the test is about intelligence, those people that are very intelligent, those that are so-so, and those that are not the smartest cookie in the jar, let's say. So what are these indicators? The item rest score correlation. So this is one method to check if an item is working well or no. The dichotomized item rest score correlation, the item discrimination index D, and all these three methods are part of the classical test theory. Otherwise, there's also a newer one, and that's the item discrimination parameter. But that belongs to the item response theory. What is the item response theory? Let's say it's a newer alternative, somehow better, kind of theory within test theory, within psychometrics. So classical test theory is basically the frame, the theoretical frame of everything we saw today. But keep in mind, there's also another newer kind of theory, and that's the item response theory. And this, the item discrimination parameter, is the way that the item response theory checks if items are good or not. But this one is something for another time, let's say. In case you want to come to the full training, we're going to go into detail for that one. But for today, we're going to focus on the tree that belongs to the classical test theory. Okay, so let's see. First of all, item rest score correlation. Now, before talking about the correlation, what is the rest score? So that's the first thing that we need to understand. What is a rest score? How do I obtain it? The rest score, it's basically saying that I want, so if I do the rest score of item 1, for example, and look at how it's written, it's going to be R minus 1. So it's basically saying that I'm going to sum up all the items, but except the one that I'm doing the rest score of. And in fact, that's why it says minus 1. So it's as if I was doing the test score minus item 1, or the test score minus item 2. So if we look at respondent 2, if I want to do the rest score of item 1, I'm going to sum up all the other items except item 1. So I basically delete it. So we're going to do 3 plus 3 plus 3. Otherwise, you can think of it in terms of I do the test score and then I delete item 1. So you sum up all of them and we get the test score, which is 13, minus item 1, which was 4. So 13 minus 4, we get 9. Whatever you prefer. Either you sum all the items up and, I don't know, take a pen or something, you hide the item column of the one you're doing the rest score of, and then you sum up all the others. Or the reasoning is, from the test score, I remove the one that I'm doing the rest score of. Okay, that's it. This is the rest score. Once we have the rest score, what we want to check is the item rest score correlation. For example, if I want to check if item 1 is good or not, I'm going to have to calculate the correlation between item 1 and the rest score of item 1. How? With the formula as always. So the fact that we need to do the covariance divided by the 2 standard deviation multiplied with each other. So all the tiny little steps that needs to reach. And this is also why another thing, it's extremely unlikely that at the exam they ask you to calculate the item rest score correlation. So I don't think that's ever happened, because once again, in the end, it's just calculating the correlation with the formula. So it's just very long and time consuming. What they might ask though is, for example, if based on a specific item rest score correlation that they give you, the item should be kept or not. What is the selection rule? Well, this one here. So depending on the specific research, they might be stricter or not, but overall, consider that if this correlation, so the item rest score correlation, is at least 0.3 up, then it's fine. If it's below that, then it's not. and we mean plus 0.3. So it's not in terms of absolute numbers. So if we were to find minus 0.4, that would be bad. So we really want from 0.3 up. The closer to 1, the better, obviously. If it's 0.3 or above, then we would say the item is working well and we would want to keep it. If it's below that, we might want to remove it from our test. Okay, now just to get an idea, I'm going to show you very quickly how an item rest score correlation would be calculated. So for example, they might ask, what is the item rest score correlation for item 3? So we have 4 items, we have 5 people. How would that look like? Just a lot of steps. Now, the first thing that we want to do is to calculate the mean of that specific item. So we're focusing on item 3 because we need to do the item rest score correlation for item 3. So for item 3, we're gonna sum up all these scores. So 0 plus 1 plus 1 plus 0 plus 1, we get 3, and then divide by n. N is 5. 0.6 is the mean for item 3. Then the first thing we're gonna do is the deviation from the mean. Why are we doing all these things? Because the correlation formula is covariance divided by the 2 standard deviation. So what I'm doing now is obtain eventually the standard deviation. So first we want to obtain the standard deviation of the item and the rest score. Then calculate the covariance and then put everything into the correlation formula. Okay, so deviation from the mean. How is that gonna look like? We have it here. We're gonna have to take the score of each person and then do minus the mean. So 0 minus 0.6 minus 0.6. Then 1 minus 0.6, 0.4. And so on for every person. The next step is to obtain the squared deviation from the mean. So basically, these numbers that we see here, we're gonna square them. And very important, also the minus gets squared. So the minus will become a plus. There's no chance that you should have negative square deviation from the mean. So all the numbers here should be positive. So minus 0.6 becomes 0.36. 0.4 becomes 0.16, and so on. The last step, and this is the formula for the variance. So if you see, what do we need for the formula for the variance? Well, we needed the mean, and that's the first thing we calculated. We needed the deviations from the mean, this column here. We needed to square them up. We did it. And then they say, add all of them up. So this column here, the square deviation from the mean, we just sum all of them and then divide by n. So 1.2 divided by 5, and we get 0.24. Okay, the last thing though, because this is the variance, but we need the standard deviation, we're gonna do the square root of the variance. Square root of 0.24, we get 0.49. Okay, we have 1 out of the 3 things that we need for the correlation. Woohoo! Okay, next thing, we need to calculate the rest score. So as we just saw, the rest score is basically summing up all the item scores except the one we're doing the rest score of. So for the first person, we're going to do 1 plus 1 plus 0, 2. Second person, 1 plus 1, 1 plus 0 plus 0. We don't consider this one. So this is why I tell you as an advice, put a pencil, a pen, whatever on top of the column. So you're not tempted to look at that number. And so on for every person. Once we have that, we're going to do exactly the same steps that we did before for item 3. So we're going to want to sum all of these rest scores up, divide by n to get the mean. Then we're going to want to do the deviations from the mean. So 2 minus 1.6, and we get 0.4. 1 minus 1.6, and we get minus 0.6, and so on. Then we're going to want to square them. So square deviation from the mean. How do we do that? Well, 0.4 squared, 0.16. Minus 0.6 squared, 0.36. and so on for all of them. Last steps, we want to sum all of them up. So we're going to sum up everything that's in this column and then divide by n. And this is the variance. But we need the standard deviation. So we're going to do square root of the variance. So square root of 0.64, we get 0.8. Okay? Almost there. We're missing just one last thing. And that last thing is the covariance. How do we obtain the covariance? Well, the covariance is basically, first of all, multiplying the deviations from the mean. So we're going to have to take the deviation from the mean of item 3, this column here, and the deviation from the mean of the rest score, so this column here, and we multiply them. So minus 0.6 times 0.4, and we get minus 0.24. 0.4 times minus 0.6, we get minus 0.24, and so on. Okay? Then what else does the formula say? Oh, once again, sum all of them up. So we're going to have to sum all of these numbers and then divide by n. So divided by 5. Okay, finally, we have everything. We have the green one, which is the covariance, and the two red ones are the individual standard deviation. Once we have those, we can finally put them into the formula for the correlation. So how is that going to look like? Well, minus 0.36, the green numbers, divided by 0.49, the standard deviation of item 3, times 0.8, standard deviation of the rest score of item 3. Okay, so this number that we see here is the item rest score correlation. Is it at least plus 0.3? No, it's very, very badly. So we would want to remove this item. On the opposite, if this had been plus 0.92, not only we would want to keep it, but we would also say that it's very good item because 1 is the maximum that we could find. So it would have been an amazing item. Okay, is this clear? Perfect. I'm gonna assume so. Okay, so before we continue, I'm gonna ask you if you could please fill in the evaluation form. You can either scan the QR code here or check your Athena profile, or you should also have a link in your email. And don't worry, it's just 5 questions. It's very fast. There's gonna be a numerical component and then a concrete feedback part where you can leave any opinion. Obviously, I always try to get rated as high as possible. Like a 9 or a 10, that would be the ideal. But if you don't think it's a 9 or a 10 yet, then please fill in the feedback. Anything is very appreciated. Any comment. Also, if we ever meet again, that's always useful. And yeah, so that I know where to improve or whatever you enjoyed. Now, I know you might have wanted to spend your Monday morning differently than doing statistics, but I do hope you enjoyed it for as much as possible. And please let me know when you're done so that we can continue with the last things for today. Okay, I see a reaction. Thank you. I'm gonna wait for the others and then we continue. Okay, perfect. Thank you. Then let's move on. Okay, so now we're gonna move on to the more likely things that they might ask you to calculate. So when it comes to the item rest score correlation, it's very, very unlikely that they're gonna ask you a calculating question about it because you saw it's not really complicated, it's just very long. But a very likely thing that they might ask you on this topic to calculate is the dichotomized item rest score correlation. How does it work? Well, first of all, we need the rest score of the item. So either you calculate it or it's going to be given to you at the exam, which is the most likely thing. And then we need to turn this rest score into a dichotomized rest score. What does it mean? Well, dichotomized, we saw it before, that basically means that it's all ones and zeros. What is the criterion for giving some people the 1 and some people the 0 on the dichotomized REST score? Well, it will be told to you in the exam, like example in the text. So they might say, we want to select 50% of the most intelligent people, something like that. So you need to look at their REST score and see which ones are the 50% most intelligent. So the 50% that have the highest REST score. So if there's 10 people, 50% would be 5 of those 10. So the 5 that have the highest REST score will get a 1 in the dichotomized REST score. The other 5 will get a 0 because being selected is the 1. So you satisfy the criteria, you pass. Well, the other, no. Okay, once we have created the dichotomized REST score, we need to create this 2x2 frequency table, which is the hardest part probably of this kind of exam question. How does it work? Well, the rows are gonna be the item. So if we have item 1, we're gonna have the first row is the ones, so all those that have a 1 on the item x1, and the second row is 0. While the columns will be the dichotomized REST score. First column is a 0, second column is a 1. Why? Well, because the important thing is that A should always be those people that have a 1 on the item and a 0 on the dichotomized REST score. B is always going to be those people that have a 1 on both. C is those people that have a 0 on both. And D, the people that have a 0 on the item, a 1 on the dichotomized REST score. Once we have this table, to calculate the dichotomized item REST score correlation, we're gonna use the Phi coefficient. And there's this very long formula, which is in the formula sheet. So once we have the table, it's literally just about making sure that we copy the correct numbers in the calculator. So we need to copy B times C minus A times D, and so on. So really the only difficult part, I would say, is to create this table. So it's just to remember how it should be built. So keep in mind, A is 1 on the item, 0 on the dichotomized REST score, B, 1 on both, C, 0 on both, D, 0 on the item, 1 on the dichotomized REST score. So item 1, 0, dichotomized 0, 1. Okay, so this leads us back to the initial exam question, the exam question that we saw at the beginning of today. Now, I'm just gonna very quickly read it just to refresh all of our minds. A researcher wants to develop a selection test to select the 20% most skilled students. He assesses the quality of the items by looking at the association with the dichotomized REST score. Based on a sample of 5 students, he wants to determine the Phi coefficient of every item. Below, you find both the item score as well as the REST score on item 3 for all 5 respondents. And then they ask you, what is the Phi coefficient? So the first step is to understand how many should get the 1 on the dichotomized REST score. Well, 20% most skilled. So you need to find out what's the 20% of 5. That or those people will get a 1. Everyone else at 0. Once you have that, 2x2 frequency table and everything into the Phi coefficient formula. So try and let me know whenever you're done. I'm gonna wait a few more seconds and then we're gonna have a look at it together. Okay, so let's see. The correct answer, as I also saw in the chat, was indeed minus 0.61. So that's B. So little side note, what does that mean? It means it's a bad item because we should be seeing at least plus 0.3. That's definitely not the case. Okay. Now, how do we get it? Well, they're gonna select, so they're gonna give a 1 on the dichotomized res score to the 20% most skill, meaning the 20% highest res score. What is 20% of 5? 1. So the one that is the highest res score will get a 1 on the dichotomized res score. And that is the person that has a score of 3. So this one gets a 1, everyone else gets a 0. Okay, once we have this, we need to create the 2x2 frequency table. So we have item 3, the first row is the ones, second row is the zeros, dichotomized res score, first column 0, second column ones. A, we know that it's those people that got a 1 on the item and a 0 on the dichotomized res score. How many are those? Well, the red ones. So 1, 2, and 3. What about B? Is there anyone that got a 1 on both of them? No, there's no one. So B is 0. What about C? Is there anyone that got a 0 on both of them? Yes, the first person here. So 1. Is there anyone that got a 0 on the item, but then a 1 on the dichotomized res score? Yes, 1. Once we have these letters and numbers, we just put everything into the phi coefficient formula. Make sure you copy the right numbers in the calculator, because at this point, once you've done that, this is literally the only mistake you could make. So make sure you copy correctly where B needs to go, where C needs to go, where A, D, and the corresponding numbers. Okay, and if you do and put everything into the calculator in the right place, you should obtain minus 0.61. Okay, is this clear for everyone? Perfect. Okay, then let's move on to the last kind of item discrimination parameter, and that's the item discrimination index D. So here, what we want to see is checking if the item is differentiating well between high and low scores. So if I'm giving a statistical question, then I know that some people are good at statistics, some people are bad. So we're gonna have a high statistic group and a low statistic group. If the item is working well, supposedly the people in the high statistic groups should get it correctly, so should get a 1. While the people in the low statistic group should get it wrong, so a 0. And this is what I'm trying to check. If indeed almost everyone or everyone in the high gets the statistic question correct, well, everyone or almost everyone in the low gets the question wrong. Okay, sorry. Now, what do we do? Well, first of all, we're gonna divide the people into the groups based on the res score. So based on the res score, I'm gonna divide them into the high statistic group and the low statistic group. So those that have the highest res scores, so overall in the test they did better, then I know that they're supposedly the most skilled at statistics. So I assign them to the high group. Those that did worse, then they're the least skilled, so I assign them to the low group. okay? And then I'm going to calculate the p-value for each group. So for each group, I'm going to calculate the proportion of people that got the specific item correct. And then I calculate the discrimination index. How? By doing the p-value of the high group minus the p-value of the low. Well, ideally, what would be this index dB? 1. Why? Well, because 1 would mean that the p-value of the high is 1. So basically, everyone in the high group got the item correctly. And supposedly, this is what should be happening. Minus 0. So the p-value of the low would be 0, meaning that everyone in the low group got the item wrong. If that's the case, the index is 1, so perfect. Everyone in the high gets it, everyone in the low doesn't. And indeed, they shouldn't. Otherwise, in general, what is the overall rule of thumb? Anything from 0.3 up is fine. Below that, the item is working badly. Okay, so let's see together an example. Now, let's see again, we have these two groups, so the high scoring and the low scoring group, 50-50. And the question is if item 3 discriminates well. What do we have to do? Well, first of all, we're going to have to divide the people into the high and the low group. How? Based on the rest score. So we're going to check. We have 6 people here. So 3 go into the high group, 3 go into the low group. Which ones are the 3 that have the highest rest score? Well, 2, 3, and 2. So these ones are in the high group. The other 3 are in the low. Once we have the groups, we need to calculate the p-value for the high group and then the p-value for the low group. Now, for the high group, we're going to do basically summing up the scores on the item. So for the I is 0 plus 0 plus 1 divided by the amount of people. Why? Because I told you before that the p-value when it comes to dichotomized item is exactly the same as the mean. Otherwise, even if we think about it, 1 means that they got it correctly. 0 means they got it wrong. How many got it correctly? 1 out of 3. So that's the proportion. 1 out of 3, meaning 0.33 got it correctly. And this is the p-value of the I. What about the low? Let's see. Well, this one got it correctly, this one got it correctly, and also this. So actually 3 out of 3 got it correctly. So the p-value is 1. Everyone got it correctly. How do we calculate the item discrimination index D? Well, p high minus p low. So 0.33 minus 1. We get minus 0.67. So again, this is a very bad item. Ideally, we would want the p of the high to be as close to 1 as possible, the p of the low to be as close to 0 as possible, so that the difference also is very close to 1, which is perfect, the highest correlation possible. Okay, is this clear? Good. Okay, so this was the last topic. Now, obviously, this was a part of the whole picture. Now, even if I was Eminem, I don't think I would be able to just put all the material of the course into 2 hours and a half, and that's why the full course it's 10 hours. Now, this is the most evident distinction. So here we couldn't cover the whole material. Well, in the full, obviously, we're gonna cover the full material. Now, also as you see today, we are small groups, so there's a lot of time for any questions that you might have. And in the full, we go through a lot of questions from past exam, just we saw today, but for every single topic. So I always mention what kind of question they might ask in theory, and then give some example of the practical ones. And there's obviously the 24/7 WhatsApp group. Obviously, if you write at 3 in the morning, I might be sleeping, but that aside, obviously your questions also get asked there. And just in case you haven't bought it yet and might be thinking about it, this is where you can find it. So if you click on the fat cat, You see the times and dates to see if they fit your schedule or anything. And if you still haven't bought it, you can use also that code to get a discount. So if you write down test Alia 40, you're gonna get a 40% discount code, which is pretty good. So yeah, in case you were interested, I would say at least check this out. And we're gonna go through everything. And then there's also a 3 hour and a half practice session where I would usually just go through a past exam. So 24 questions from a previous exam, and you can really use that as a simulation of where you are at. Okay, so this was it for all the content of today. Do you have any questions about anything we saw today? Anything more practical? This is your moment to ask. And then I will set you free. Okay. Then I wanna thank you for having been here today. And if I'll see you at the full training, then see you tomorrow. Otherwise, I wish you very good luck on your exams and happy holidays. Okay. Bye, everyone.
Thank you. Bye.